right, so for the next problem, I think I assigned 22, which is easier than 23. 23 and 23 are very similar, so let me go over number 23. So it asks, what is the probability that a positive integer not exceeding 100 selected at random is divisible by 5 or 7? So we have to remember this rule. This is or, so we have to consider both cases. Okay, so let's start to think about it. It has to be positive integer not exceeding 100. So it's going to include a number below 100 that is divisible by 5. It's going to be 5, 10, 15, and so all of these numbers. And there are going to be 20 of them, and we can easily find this by doing 100 divided by 5. And there's going to be 20 of them, so we're going to keep that number for now. All right, so what about a number that is divisible by 7? So we can start to list out. It's going to be 7, 14, 21, 28, 35, and so on. So again, we can divide this just to find the number of those numbers, these numbers that's divisible by 7. So if we do this, this is going to be 14.285. So here we're just interested in knowing the number. So there's going to be 14 of them. So we'll keep these two numbers. Now, if I were to write this a little further, 15 and so on, and we know that there's going to be 30, 35, and it goes on. So what we notice is that some numbers has been counted twice, and those numbers are part of these counts. So what we have to do is we have to exclude them, and then we can refer back to our Venn diagram. This was divisible by 5, and so x is divisible by 5. So it should be the other way. The 5 divides the x, and this is the portion where 7 divides some number y. Okay, and we have this portion inside where it's both divisible by 5 and 7, and this is going to be 35 divisible by some kind of number z, because 5 times 7 is 35, and we need to count how many they are in this union section. And to do that, here we can just follow our process again and do 100 divided by 35, and there's going to be, this is 2.85 something, but that's not, the remainder is not what we're interested in. There's going to be two whole numbers between under 100, that's probably going to be 35 and 70, that has been counted twice. So what we're going to do is, keeping this x, y, z intact, we're going to do number of all the x values plus number of all the y values, and we're going to have to subtract the number of z, okay, because that have been counted twice, and we can kind of see it. Number of x is all of this, and number of y's has been all of this, and you can see how this union, the intersection, has been counted twice. You just have to subtract one time. All right, so we can do this by doing 20 plus 14 minus 2, and this is going to give us 32. So this is it. Out of 100, there are going to be 32 possible numbers, and these numbers are going to be divisible by 5 or 7. So our answer for this problem is going to be 0.32. All right, so next up is a pretty interesting problem, and it's pretty famous in statistics. I don't know if you have heard about this problem or not, but it's called the Monty Hall problem. It's based on this TV show that it's even old. The show itself is even old for me. I've never seen it, but here's the general rule. And I'll attach a video that also explains it, so if you guys want to see that video, you can. So there's a show where if you come in, you're faced with 3 doors, and it's called the Monty Hall problem because the show host's name is Monty. All right, so you have a door, let's say A, B, and C. And behind these doors, there are 2 goats and 1 car. So if you pick a door where behind there is a goat, then you don't win anything. But if there happens to be a car sitting behind it, then you win the car. So for the longest time, the people have believed that, well, if this was a fair game, then the probability of winning a car is 1/3. All right, but here's the trick. So let's say you picked door A. So you're standing right here. The show host, Monty, is gonna ask, he's gonna actually show one of these 2 doors that has the goats in it. So one of them must be, if not all of them. So he's gonna open, let's say that our choices were car, goat, and goat. Okay. So here, Monty has a choice. He can either show, open door B or door C. Okay. But let's say that the case was actually goat, car, and goat. If this is the case, Monty's going to go ahead and open up door C. All right. And of course, the goat is revealed, and Monty's going to ask a question again. Do you want to switch your door? Okay, do you want to switch? So this option is now out, and he's going to ask, do you want to switch or do you want to stay? Okay, this would have been a good choice where you had, if you had made a choice to switch, then you would have won, you would win the car. But in our first case, with the first initially I wrote goat, car, goat, and goat. Okay, if that was the case, then this person, the player, should have stayed, right? It should not have made a move because the goat would have been revealed and the initial choice of the car would be gone. Okay, so that's the overall understanding of the game. And for the longest time, people thought this was the right answer. Wherever you choose or if you decide to make a change after the reveal of the door, it's still, you're gonna have the same probability, which I think is very intuitive. But here's the solution that one mathematician actually said. The mathematician claimed that the player should always choose or should always switch when the other option is revealed. And that's going to give a much higher probability of winning a car. In fact, if you make a switch, then the probability of winning a car becomes 1/2 instead of 1/3. So it becomes from 0.3 or 33% to 50%. And here is the reasoning why. I think most of the videos that I tried to find the good ones on the YouTube had a slightly different interpretation, so I'll provide another one that hopefully this will make more sense. All right, so let's have door number 1, door number 2, and number 3. Okay, and let's pretend that the player will always pick door number 1, okay, no matter what. All right, and so here are our 3 cases. It could be the goat, goat, and the car, or goat, car, goat, and car, goat, and goat. All right, so let's take a look at the first case where the player picked the first door. So the player is here right now. He's standing behind door number 1. Okay, and let's have the option of staying with the door number 1 choice versus switching. Okay, and this mathematician's claim is that the player should always switch. This is going to give a higher rate of winning. All right, so let's see if that's true. So right now the player is had unfortunately picked the goat. The Monty knows what's behind these doors. So Monty's going to reveal door number 2. And the reveal showed that, oh, it's not a goat, and the Monty asks, would you like to switch to door 3, or do you want to stay? Staying would result in the goat. Switching would result with the car. All right, so this would have been a good move to switch. Let's see our second case, where the lineup behind his doors is goat, car, and a goat. So now the player is still picking door number 1, and Monty approaches, and asks or shows, in this case Monty only has one choice, which is to show number 3. All right, so he has shown door number 3 and asks, do you want to stay with your original choice, or do you want to switch? Staying will result in the goat again, and making a switch would get to a car. All right, so again, for this case, switching would be a better move than staying with door number 1. Let's take a look at the last case. This is a case where you picked door number 1 and the car behind it happens to sit behind it. But of course, we don't know that. None of us know that unless you're Monty, and then Monty comes and decides to reveal. He can reveal any of these 2 doors, but let's say that he revealed door number 3. Okay? And door number 3 is revealed and asks you the question, do you want to switch or do you want to stay? And if you stay, then you're fortunate. You have won the car. But if you make the switch, then you end up with the goat. All right, so here's the case. By making a switch, you win the car. The probability of winning the car is 2/3. And not winning a car is 1/3. This is higher rate than if you stay, then the probability of winning the car is just 1/3. Okay, so because of this probability, which is highly unintuitive, it's much better for the player to make a switch rather than stay behind the original picked door.